Hi there. Thanks for joining us. This is Space Nuts. We talk astronomy and space science, and sometimes we talk about things that have got nothing to do with astronomy and space science. You just never know. We throw up all sorts of things, and sometimes we throw up. Today we will be talking about SpaceX. They're in the news again, and it's all about the numbers. And I'm not talking their share price. Well, actually, I probably will. Educating the public about the real moon. It's an issue that NASA thinks needs to be dealt with. We've got a 3i Atlas update. Yes, you thought it was long gone, never to be spoken of again. Not true. Fascinating facts have been revealed about this amazing little rock. And and we might have to start again.
I'm sorry.
Or I can cut this bit out.
Just cut that bit out. I'm sorry. Marnie's just got back from walking the dog.
Hi, Marnie. We might leave that
she
bit
can't
in.
Hear you. Yeah,
that's okay. And what was the last thing? Our son's death
I've already
spiral.
interrupted it. So.
G'day.
Sorry.
There she is. You're right. It's all good.
He says
It's all good. It's only the intro.
It's only the intro.
Yeah. Not an important bit. Anyway, whatever I was talking about is all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Takes me back to my old radio policy. If somebody walked into the studio, they were on the show.
On the
and
show.
That's exactly what happened. And joining us, aside from Marnie, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Sorry
Good
about
thing
that.
you're here. That's okay.
I'm glad
I
I'm
don't
here.
mind. I don't mind. I used to work with some radio people who got so annoyed if they were interrupted for any reason whatsoever. We even had one guy who wouldn't even accept you looking at him through the window.
Really?
Yeah.
Whoa.
He used to get really steamed.
From the producer suite through to the...
Yeah.
Yeah.
When he was in the studio, you weren't allowed to go in and you weren't allowed to look at him through the window. 3 solid hours of isolation. It was... and, sometimes you'd do it accidentally.
Of course you would, yeah. Yeah, of course you would.
Yeah, they were fun times.
Yeah.
Yeah. So Marnie's well, and you're well, and everybody's well.
We're doing all right. That's right.
And something else that's doing well is SpaceX. Probably not their share price, which is currently showing what they call correction, but it hit a massive high not long after the company went public. But now it's, what do they call it? Adjusting. Yeah, adjusting.
Yeah. It's those numbers are a bit alien to me. As I've said before, I only understand billions when they've got light years after them, but they have dollars after them. And I've watched the fortunes of SpaceX since the IPO. See, I'm in the jargon there. The initial public offering. Oh yeah, yes, you're right. It looks as though it's going to be back where it started. I think the way things are going.
That's generally what happens, and sometimes they keep going below that, and they bounce back later. I find it really bizarre that we base our entire wealth and future on something as volatile as the stock market. I've never understood that side of the business world, and your whole retirement is based on this stuff. In some cases, and especially in Australia with our superannuation system. And, you could just be I've known people who were just about to retire and there'd been a big crash and they had to work another decade. It's just, gosh. Ooh,
wow.
Scary stuff. Anyway, we're not talking about that today, even though we were talking about that today. We're talking about something else to do with Elon Musk's company SpaceX, and that is that they have they've basically set a space launch record.
They have. It's really quite a milestone when you think about it. What they have done is launched 15,262 satellites as of June the 12th. I mean, they're launching so many. You've got to pick a date for it. But June the 12th, 15,262 satellites. But here's the rub. Here's why it's a record. The combined total of all other companies and organizations since 1957, when Sputnik 1 was launched, is 15,138. So SpaceX has now launched more satellites than anyone else in history.
Combined.
That's
wow.
Right.
So they've more or less doubled the number of satellites by themselves.
That's right, except a lot of those
they're not up there anymore.
A lot of those aren't up there anymore. I think they have. I think it's about 11,000 operational Starlink satellites at the moment. But there's 1,000 more that have re-entered and 1,000 more that are not activated yet. Those are the sorts of numbers. So it means the total. Few days or a few weeks since I looked at this figure, but it's about 15,000 altogether is the number of operational satellites, with, of course, huge numbers of ones that are no longer operational and even more numbers of bits of space junk that you can't track. But yes, what a extraordinary record. And of course, what's brought this what's brought SpaceX to this milestone is the Falcon 9 rocket, which has been so successful. They're now reused. I think the record is still 33 for the number of times a Falcon booster has been reused. That would have been unthinkable not much more than a decade ago. It was 2015 when they had the first recovery. Really quite remarkable. So there were 165 Falcon flights in 2025. That's 3 a week basically, isn't it?
Yeah. That's incredible. And of course, he's talking about that supercomputer satellite system that he wants to create, and that's going to put many, many more up there if he goes ahead with it.
It's 1 million, that's right, which is eye-watering in many ways. It makes you shed tears if you're an astronomer.
Yeah.
That's
basically for artificial intelligence systems, isn't it?
It is, yes. It's their plans for an orbital data center with 1 million linked satellites. And what will enable that, what will facilitate it, perhaps that's the word, is the next step, which it's already been tested out, is launching these satellites using Starship rather than the Falcon. Because Starship Falcons, typically they launch about 20 at a time, 20 Starlink satellites at a time with the Falcon 9. It's when you move to Starship, you're talking about much, much higher numbers. I don't know how many they could launch, but it's probably well over 100, maybe even in the 200s.
Wow. I know astronomers wouldn't be happy with another 1 million satellites up there crunching AI data, but interestingly enough, we were talking to our son the other day who works in, I suppose you could call it the gross retail area of electronics. Mm-hmm. And he is frustrated at the moment because he'll get a client that wants quotes on various electronic items, and we're talking smartphones, other smart devices. And then when the order comes in, the price has been hiked because of a lack of random access memory available because it's being chewed up by AI companies.
How interesting. Yeah.
So there's a world shortage of RAM and DRAM and a few other memory chips that are required for household devices like computers because they're all being eaten up by these AI facilities. It's a bit of a problem at the moment.
It's a good point. It hadn't occurred to me that there might be a shortage of that sort of thing. Because,
and it's hitting the household market.
Yes.
The people who want to buy a computer for themselves at home are facing price hikes because of this. So it's a thing. It is a thing. So maybe Elon's found a way around that, or maybe he's getting all the chips. I don't know.
Well, I think that's what it is. If the AI companies have got first dibs on the memories for the data centers, that's where it's all going to happen. Yes,
it's like when I was at school, Fred. You don't share your chips.
You were lucky to have chips. We didn't have chips when we were at school.
We used to live in a tin can. Oh, boy. So, yeah, things are steadily moving along for SpaceX, and they've achieved a major milestone, which probably won't stop there, but they're 100 ahead of the collective number of satellites put into orbit around Earth since 1957. They've doubled the number and some. It's and probably will continue. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, your labs are here also.
Space Nuts.
Our next story takes us to the moon. It's kind of in fashion again now, particularly with the Artemis program and the recent mission to fling people around the moon and take some pretty pictures and witness some of the amazing things that happen on the moon. However, NASA believes that things need to be done properly in terms of educating the public. Why is this happening?
It's the initiative of a professor of astronomy and planetary sciences in the Department of Physics at the University of Central Florida, whose name is Daniel Britt. And he's very well up in what it's like on the moon, because he's director of the Center for Lunar and Asteroid Surface Science. So they had what they call a Space Resources Roundtable earlier this month, and this month being June 2026, at the Colorado School of Mines. And that sort of gives you a bit of an idea where this is coming from.
Yeah.
So Professor Britt, Daniel Britt, says, and really to put this in a nutshell, to put the nub of the story, he says, I wish I could say that engineers and managers know better, but they don't. We are training a generation of engineers not to worry about terrain. If the artists are getting it wrong when they depict the moon, it's our fault. Let's stop fooling ourselves. And basically, he went on to complain about a number of the sort of artists' representations of the lunar surface, which are promulgated by commercial space ventures, but also NASA. And I've actually had the same thought. I've seen some of NASA's artists' impressions of, a base on the moon and what they look like, and thought that all looks very, very neat and tidy. Very neat and tidy indeed. And so what Daniel Britt has done is kind of highlighted all the things that are wrong with those pictures that might actually transform the way we think about the lunar surface.
Why is that such a problem, though? Is this going to, what does it change?
So it's the reality is different from what we depict. So if you're always depicting the lunar surface as something neat and tidy, and you're training your engineers who are building the spacecraft and doing all the rest, setting up all the infrastructure, then they've got a false idea of what it's like. And so what Daniel Britt has done is highlighted some of the problems that in those illustrations, starting with small craters and the lunar dust. It goes on to talk about dirty astronauts, dirty equipment, and dirty habitats. And you've only to look at some of the imagery from the Apollo missions to see how dirty the astronauts get, because that dust gets everywhere. It's, as it said, captioned to one of Daniel Britt's images, dust is a factor of life in lunar ops. It gets everywhere. And so, we've got the Apollo experience to judge from. And it's also going to be much more difficult to cope with the dust in the Apollo programs, because you're in the South Polar region of the moon. That's where, not Apollo, Artemis. Artemis is concentrating on the South Polar region of the moon. And that means you've got a very low sun angle. And the dust is just going to be everywhere. You will, so you might have interference from the dust, but also if you're walking around on the surface, it's going to be very easy to miss because of the lower sun angle. The sun's always in your eye. It's going to be very easy to miss little craters, and there are small craters everywhere. It's a really difficult environment in that regard. And he goes on to sort of spot the other things that are going to be problematic. One of them is the number of boulders there are as well on the surface. It's got the Apollo images, he says, were taken down sun. In other words, you're looking with the sun behind you.
Yeah.
And that it sort of hides all the shadows of all the boulders and things that there were lying around. I mean, we've talked before about how lucky Apollo 11 was, because there were, when Neil Armstrong was bringing the lunar module down onto the surface, all he could see was all these boulders.
Mm. Yeah, and I'm just looking at a real image of Apollo 15, and they had a dicey landing as well. They actually landed on a piece of ground at an 11-degree tilt.
That's correct. Yes, that's the other one of the other issues that he's highlighted is the tilt of the terrain that you land on. Apollo 14, 7 degrees, Apollo 15, 11 degrees. And yes, that's quite a serious angle.
It is.
And that does not go well if you've got a very tall landing craft, which is what the SpaceX's Starship will be. Starship, the lunar lander. That's one of the two landing vehicles that are currently being considered by NASA. I can't remember what it is. I think it's 37 meters tall. It might be even taller than that. It's enormous. And if you put that on an 11-degree tilt, you're going to be worried that the thing's going to fall over, which would not be good news.
You're going to have to pick a really, really good spot, and they're few and far between on the moon. And I can imagine a vertical landing craft like that, a very tall rocket, is going to blast up dust like nothing else.
Yep. That's right. And in fact, I think there's a quote from one of the Apollo astronauts, because of the amount of dust that was being blown up by their exhaust as they were trying to land, they couldn't actually see where was the safest landing point.
Yeah, that's scary, isn't it? And not to mention that dust is one of the big perils of electronics.
Yes, that's right.
You don't want dust getting into anything. In fact, I think in the early days of home computing, one of the big problems was you had to keep your computer cool, but in doing so, you're sucking dust into the machine, and that could get into the processors and the drives and all sorts of trouble. In fact, if you ever open up a home computer, particularly an old desktop, first thing you notice is all the dust.
Yeah, that's correct. Yes, which has been sucked in, exactly as you've said.
Yeah.
If I can, there's a couple of paragraphs that really sum up Daniel Britt's view of all this. And remember, he's a professor of lunar surfaces, so he knows what he's doing. Yes, he says these are artist's impressions, but somebody is telling the artist what to draw. I love the idea of landing and operating on a moon without dust, small craters and rough terrain. However, we see the misconception of a flat, gentle moon everywhere. Commercial providers are just as bad. No dust, almost no small craters, no tipping problems. Yes, these are artists' impressions, and getting it wrong. NASA knows better. All these people should know better, but don't. Let's not fool the public. We owe them better data. He's really having a go about it, isn't he?
Well, I think he's got a good point.
He's got a very good point. Yes, he has indeed.
We might go on holiday there one day and we'll turn up and go, this place is crap.
It's a dump. Yeah.
Where's the pool?
Oh, yeah. For that.
It was in the brochure. But no, I see his point. And I suppose organisations like NASA, who have basically led the race to the moon since the year dot, probably should just take a bit of notice of what he's saying. Yeah. For sure. If you'd like to check that story out, it's a good read. It's at space.com. Let's move straight on to our next story, Fred. And this one is, something we've spoken about several times recently because it was a pretty exciting find. That was Comet 3I Atlas. What brings it back to the fore? I thought it was all dealt with and gone and on its way to wherever the heck it's headed. But it's back in the news.
It is back in the news, and I think it's back in the news. This might be never say never, but I think this might be the last major paper about 3I Atlas and its composition and what we now know about it. And it comes from a number of studies, principally using the Webb telescope. These are analyses of the outgassing, the material that's being outgassed from 3I Atlas's surface. Remember, it's an interstellar asteroid. It has entered the solar system last October, I think, was when it was discovered, zooming through at speeds in the region of 60 kilometers per second, which is too fast for it to belong to the solar system, and it's now on its way out. But a lot of resources have been used to observe it because it's a free gift from another solar system, the fact that we've got this object coming through. And so the analyses that have been done are really very, very interesting in terms of what they tell us about the wide blue yonder, about the chemical composition of solar systems other than our own. And in the same breath, it sort of tells us a bit more about our own solar system, how unusual it might be, because this is something quite different. So the two studies involved are one which was conducted using the Webb telescope, and the other which was led by an astronomer from the University of Edinburgh, which was one of my alma maters. That was using the Very Large Telescope, the VLT, at Cerro Paranal in Chile, the European Southern Observatory's major facility. And what they've done is essentially looked at isotope ratios. They've looked in particular molecules like H2O, water, CO2, carbon dioxide, CO, carbon monoxide. And there's a plot which is on. It's actually basically NASA's press release about this. The press release is titled "NASA's Webb finds clues to ancient distant origin of Comet 3I Atlas," and the plot shows sort of the isotope ratios. It's basically too small for me to read the individual numbers on it, but for all the solar system comets that have been observed, including, I notice, Comet Hartley 2, which is one discovered by my old friend and colleague Malcolm Hartley. It was visited by a spacecraft a number of years ago. He became a international celebrity because of that. We used to work together at the UK Schmidt telescope. But that's one of the solar system comets that they highlight in this plot. And you can see that the various aspects, notably what are called heavy carbon and heavy hydrogen. So these are different isotopes of carbon and hydrogen. Yep. You can see where they sit in the solar system. This whole line of red circles, which are representations on the plot, all in a neatish line anyway. And then way off to the right, at much higher ratios of carbon-12 to carbon-13 and much higher ratios of heavy hydrogen to normal hydrogen, which we've talked about a lot. But way off to the right is 3I Atlas. So
that's saying the concentrations are more significant.
They're very, very different.
Yeah. Different
concentrations of the isotopes. And that basically suggests some of the issues on the history of the comet. I might read a little bit because there's some very nice summaries here on the press release. So one of the instruments used on the web showed only traces of carbon-13 compared to lighter weight carbon-12. This points to a very old origin for 3I Atlas, as stellar systems become enriched with carbon-13 over time as generations of stars are born and die in the galaxy. So why there are higher levels of carbon-13 in our system around our sun, which formed relatively recently, 4.5 billion years ago. It also says there were exceptionally high levels of deuterium, about 30 times more than seen in solar system comets. This implies that 3I Atlas may have originated in a very cold system much earlier in the history of our galaxy. So that these are all clues about the origin. And once again, reading from the press release, the research team estimates that 3I Atlas could have formed as long as 10 to 12 billion years ago.
Wow.
During the universe's cosmic noon, when star formation was at its height, its young origin solar system was likely ensconced in a relatively cold, dense cloud. The abundance of heavy water shows that 3I Atlas spent its formative years in a deeply frozen state. This is quite extraordinary.
Amazing, yeah. It's come from a place that was very different to now, and I guess that's the difference in terms of the time scales we're talking about. What it was like then, what it's like now.
Yes, that's right.
It's like a little time machine.
Yeah, yes, exactly. It's a time capsule. It's a lovely time capsule. In the way it's been analysed. I'd have to say I take my hat off to all these scientists for the imagination that's been used in devising the experiments that have been developed. You know, these observations tell us quite unequivocal things about this object which we would not otherwise have known. And it again highlights just how different our own solar system is to probably most of the other solar systems that we can look out of beyond our galaxy and see. Something formed 12 billion years ago, that would be very, very different from the universe that we see now.
I think it's incredible that in this day and age that we can look at a rock hurtling through space at 1.4 billion kilometres distant or wherever. You know, I think it was closer than that at one stage, but you know what I mean?
Yeah.
And be able to break it down and say, this is exactly what we're looking at. And because of that, we think it came from, the early universe. It's just incredible. And a great story to read, which you can do at the NASA website, science.nasa.gov. You can also read the paper, which was published in the journal Nature. This is Space Nuts. Andrew Dunkley with Professor Fred Watson.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
Space Nuts.
The other day, Fred, in one of our previous episodes, we talked about the death of our sun and how it'll turn into a red giant and fry us all and, free barbecue gas, but that's about it. And we've had questions about it as well. Now there's some new information about the death spiral of our nearest star, and it's a bit weird.
It is. There's a very nice space.com piece on this written by Robert Lee. I love Robert's headline, "Our sun is destined to kick and spit its way across the solar system when it dies."
Yeah. Great.
That's right. So the first sentence is, scientists have discovered that dying stars don't go down without a fight.
Well,
yes, I like that theme very much.
We shouldn't be surprised by that.
Not really, no, that's right. So what this is about is the later stages of the sun's life. It seems inevitable from what we know about the way stars behave that within the next 3 to 5 billion years, the hydrogen in the core of the sun will run out, the core collapses, and the outer layers of the star basically puff outwards, perhaps making the star 100 times its original diameter. So, our sun's going to get very big, big enough probably to swallow up the Earth. And what you get is you get a planetary nebula forming. That's what we call them. That's that circle of glowing gas or sphere of glowing gas with a white dwarf at the center. Probably, actually, the sun might even be as big as the orbit of Mars when it goes. But it's a person at California Institute of Technology, Jim Fuller, has calculated that during that process, before the star becomes a white dwarf, it basically spits. He says it will receive around 10,000 little kicks over the course of hundreds of thousands of years. So they're well spaced out. But these are blobs of plasma that are being ejected from the surface of this bloated version of the sun, the red giant. And the point that Jim Fuller is making is it's a good one. It's basic physics. If you eject a blob of matter from the sun gets a kick in the opposite direction.
That makes sense.
Newton's law. For every action, there's an equal and opposite reaction. And so these, he suggests, will push the sun around in different random directions. What is technically known as a random walk. So basically, random walk is, as the title suggests, you basically randomize movement in any given direction, and you end up with this random walk process. And so Jim Fuller said that for a red giant, the random walk would basically, each of these spits would see the thing moving the sun moving at around 3,540 kilometers an hour.
Whoa!
Now that's a lot in terrestrial terms, but when you think about stars that are collapsing into basically black holes in supernova explosions, which the sun won't do because it's not big enough, that's still a very small velocity, but it still produces a random walk. I think that velocity is actually the overall motion that you get from this random walk process. You get it actually moving in a random direction in space.
So it's going to kick and scream and go down like, I don't know, a heavyweight boxer. It's not, and it's going to bounce around the ring like,
yes,
yeah, Muhammad Ali.
Yeah, or even Cassius Clay.
Or Cassius Clay, whichever you like.
Yes, same person.
Definitely. Okay. Well, I guess the question is, how did they figure that out?
Yes, so I think that's, what you do is you look at the thermohydrodynamics of the interior of the sun as its atmosphere is changing. There's in fact, I should say the atmospheres of stars are an area of research that has been really very well studied over the last 50 years from a theoretical viewpoint. And I've sort of watched the way that evolves a bit, because my job at one stage as the project manager of the RAVE survey, the radial velocity experiment, which we carried out on the UK Schmidt, measured the spectra of 500,000 stars. And a lot of what we did with that was to do with the atmospheres of these stars. And I kind of watched the way the technology evolved and all the buzzwords that, I mean, I didn't understand the science because I've never really dwelt on the interiors of stars in any deep level, at least not as far as the hydrothermodynamics are concerned. But the buzzwords that they were using changed over the years, and the codes, the software that was being used to make these analyses, and so they're well understood. And I guess it's a deeper analysis of that gives rise to the idea that you get spits. And perhaps I can suggest the direction that might have come in, because normally when you think of the atmosphere of a star, you imagine it as something. The atmosphere is basically in shells, different shells. You can imagine its structure changes, but you always imagine it to be completely spherically symmetric, that you're talking just about spheres. Now, if you break those spheres down, then you're going to get different processes going on at one side of a sphere from you get at the other side. And that might be where these phenomena originate in what Jim Fuller's talking about.
Fascinating. You can read all about it at space.com. It was presented at the 248th meeting of the American Astronomical Society in Pasadena and has been submitted to the Proceedings of the Astronomical Society of the Pacific. So, it's a fascinating discovery, and glad we won't be around to see all that. Yeah. Fred, we're done. Thank you so very much.
Thank you, Andrew. It's been jolly, as always, and hope we can do it again sometime.
Maybe in a few minutes. Who knows? Professor Fred Watson, astronomer at large. And between episodes, please visit our website or our social media platforms, and maybe go to the podcast group and have a chat with other people that listen to the show. And they quite often talk about what we've talked about and carve it all up between themselves, which is good. And you can check out all our other stuff on the website as well, spacenutspodcast.com. And thanks to Hugh in the studio, who couldn't be with us today because he proved Newton's law. We turned up, so he went the other way. And from me, Andrew Dunkley, thanks for your company. We will see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.